All right.
Yeah, I won't cry by myself.
So it seems we haven't got a lesson Friday. We need to just no.
Just what I wanted.
Right, thank you. All right, so yesterday when I introduced the logs, we showed you the graph and we introduced the being the inverse of each other. So y equals log this is a base e of x I'll use. So it's the inverse y equals e to the x. And as I mentioned yesterday, the graphs of these are a reflection of each other in the line y equals x. Right, so that would look something like this. Alright, so the line y equals x is this red one. The graph of e to the x, and we go through the y-axis at 1, because anything to the 0 is 1, and if I choose another point, and the other point that I can choose would be the point where x is equal to 1, and so where x is equal to 1, y would be equal to e. So that point there is 1 and e. Alright, so if they are a reflection, then, so that blue one there is y equals e to the x, and reflection in the y-axis. So this intercept gets reflected over to there. This point here gets reflected over to here. And so the coordinates of that point is it's now e and 1. So I quite put it in the right spot. Put it in the right spot. E and 1. That's 1. It goes like that. So log graphs, unless they've been translated, intersect the x-axis at 1, vertical asymptote, and they curve around that way. Sorry.
Is that orange line y equals?
Yep, I haven't put that. That orange line is y equals log to the base e of x. Alright, so our features of log we have an x-intercept, or f of 1, is equal to 0, so that's our x-intercept. The y-axis is vertical asymptote.
You missing tongue. That's nice to know.
The domain of log graphs is up here, R plus. And our range, of course, can be anything. So all real numbers. And then, as I said, we can transform them like we can transform any graphs. So let's have a look at a couple of examples.
So, whatever the y-intercept is the vertical axis?
Yeah, so the y-intercept, when we reflect it, becomes the x-intercept, yes. Is that what you're asking?
No, like what does the y-axis vertical asymptote mean?
Well, the y-axis, the log graph has an asymptote there, so the asymptote is the y-axis.
Is it though? Is it the... Oh, okay, yeah. Okay, that makes sense.
So for e to the x, the asymptote was the x-axis, so then when we reflect, that gets reflected to there, this end gets reflected to there, so the asymptote is the y-axis.
Does that mean that the asymptote will move,
Correct.
but vertically? Like vertically, it's still like vertical but moving side to side. Okay,
Yep. So if you have translations in the x direction, yes, the
Yeah.
asymptote moves as well. Oh, can I rub that off yet?
I reckon.
All right, let's do an example.
Are you going to that? Why don't you delegate someone to go? It's like the time I was interviewing once and then it wasn't on.
Make sure.
It's like, thank you, Eleanor. Pardon? She can be school girls or
All right, so what we have here is why it's locked to the base 2. We'll worry about the base 2 later. But locked to the base 2, x minus 5 plus 1. So there's some transformations here relating to these two things. So what are those transformations?
Up one.
Up 1, yep. So it's a translation.
Right side.
Yep. Up 1 and right 5. So if it's to the right 5, our asymptote will be, instead of the y-axis, it will be moved
To the X.
x to the x equals 5, not y equals 5. Vertical asymptote, vertical line, so x equals. So asymptote of x equals 5. Alright. So, what have we got? Got something like this. Right, so we have a vertical asymptote here. X equals 5. Now the other thing that we would have is it's moved to the right 5 and up 1. So remember the normal log would normally intersect here at 1 on the axis. So if we move that to the right 5 and then up 1, okay, so again, your normal log without any translations usually would intersect there. And we go like this. And it's moved to the right 5 and up 1, so this point here is now there.
So it's 6, 1.
So that point there is 6 and 1. Right. And so now we can say that it goes around like so.
Would you suggest finding those points?
Find an x-intercept, we could find an x-intercept. So if we find the x-intercept, y equals 0, so 0 equals log to the base 2 of x minus 5 plus 1. Take 1 from both sides. Rewrite that as a, no, not a quadratic, a
It's like rule number.
yeah, exponential equation. So what's the exponential equivalent? 2 to the
To the negative 1.
2 to the negative 1,
Equals
x take 5. 2 to the negative 1, what's that? Half. So half plus 5. So our x-intercept is 5.5 or 5.5. All right.
Or would they want you to put it as an improper fraction?
Probably should be as an improper fraction, yes. But probably should have it as 11 over 2 and 0. And there you go.
That's the end.
That's the end of that. Oh, now applied domain. And state the implied domain. So, implied domain just means what's the domain of this thing? The domain of this thing is?
All real numbers.
Not all real numbers. Can't have stuff down
5 to the
here.
square
5,
5,
no,
not inclusive.
5 not included, all real positive numbers.
Alright, so implied domain. There's 2 ways we can write it. We can write it in set notation, like that, or you can write it like that.
How come it has not a square one?
Because it never touches 5.
Because it's 5 is the asymptote, so theoretically it doesn't touch. It gets closer and closer and closer. Doesn't actually get there. Alright. Now, on your calculators, you can enter anything with any base, but not always can do that, so there's a change of base thing, and we need to do that because it's mentioned on the course. So we'll do that and then we're done. Alright, can I rub that off?
Yes.
Alright, change of base.
How do you get the name? What do you prefer to mention? I think of the metal one.
We're teaching my baby cousin to like reading books.
How much money is going to take up?
No, my cousin will. Probably not. In the Taylor family it is, no. By baby I mean like not even one, so I don't know.
Alright, if you want more info on this,
No, really don't. Yeah.
you can look at page 231 in your text. Alternatively, you can just use it. So, for logs. If you have, so log to the base A of x, you can change the base to something that's more useful, call it b. And to do that, it's log to the base b of x divided by log to the base b of whatever your old base was. So if you had a calculator where you couldn't do any base, at only base 10 or base e, then you would choose this base here to be, base 10 for example. So, for example, if you've got log to the base 3 of 5, a lot of calculators can't do base 3, so you would use this. And you would choose, say, log to the base 10, log to the base 10 of 5, divided by log to the base 10 of 3, and whatever that works out on your calculator is what log to the base 3 of 5 would be. Now, there is an exponential equivalent to that. So if you have a to the x and you need to somehow change that to another base, the equivalent is b to the power of log to the base b of a times by x. Yep, I know, not overly.
Not master at all.
So this top one here, the log one, you probably see that a lot more often than you will this exponential one. So what that means is 3 to the x would be the same as 10 to the power of log base 10 of 3 times x. So if you need to use a calculator, you might need to do that. Now, what this one here can be used for is helping us find the transformation that takes place. All right. So let's do an example. That's it. Okay. All right. So here we've got two exponentials. One is y equals 2 to the x, and the other one is y equals e to the x. So very similar, except that all this number here does is changes how curvy it is. It's more like this, or the wrong way. Flatter.
Sorry, what?
I'll just go that way, that's a log, so it should go this way. Alright, so all a number does is whether it's a shallow one or whether it curves more faster. Alright, so there's a transformation. Now, looks like that the transformation is some sort of dilation, doesn't it? Because this point is not changing. So, what's and not a dilation from the x, because that point would move, so it looks like it's going to be dilation this way, because this point here on the y-axis doesn't move. So what we need to do is we need to get these written in a similar way. So the first one here is base of 2, whereas the second one's base of e. So if we can rewrite this one here with the base of 2, we'll then be able to compare and see what's been done to that to get that. So using y equals e to the x, we want to change to base 2. And so this is what we would use to do that. So in this case here, A is E and B is going to be 2. So if we have e to the x and we follow this, we want a 2 to the power of something. 2 to the power of what? Log to the base b, which is 2, of the old base, which was e, times by x. Alright, so we've rewritten this one with a base of 2.
What's that with the little 2?
That's the little 2 there.
Yeah.
Log to the base 2.
Log to the base 2 of e. So log to the base 2 of e is just some number. So we've got some number in front of the x. And what would this, a number in front of the x, what sort of transformation is that?
What's the dilation?
Dilation from the y-axis, which is what this looks like. So it's a dilation, say this point here either goes to there or it goes to there. Dilation. So we've got a dilation from the y-axis. And what's the other thing we've got to remember about dilations from the y-axis?
It affects the x.
Affects the x.
This is relatively simple. So it can do this.
To be honest, it was relatively simple before.
Now, factor what?
2.
No, not factor 2.
Half.
Factor, whatever that is.
Because the number is this one. This is the number.
Is it 1 over?
1 over, yes. That's what I was trying to get at. When there's dilations from the y-axis, the factor is 1 over. All right.
No.
It's pretty unfair.
The factor in front of x is always 1 again.
Yeah, so that's how I remember it too. It's always 1 over.
Is that a big?
If it's in front of an x, it's just weird.
Sorry?
On the bottom is, you see like the E? Is that an on top E or a big E?
This
This E is the same size as the log. The 2's a little subscript, and the E's the same as the log.
Okay.
Just looks like it's higher up.
I don't know.
I know, it's just the way I've written it because I'm
But if it is
I'm
the same,
artistically challenged.
but if it is the same as the one up there, then you can see that they're
It's
on
the same as the one up there.
Oh, okay, that's
They
right.
are on the same level.
That one there and that one there, they're supposed to be the same. I know, and I got my pen licence when I was in primary school. I just waited till the next year and then I just used a pen anyway.
Well,
I feel like that happened to me
I
as well.
took too long to complete
All right.
like writing tasks.
But as Eliza said, if it's, thank you, listening. As Eliza said, the pattern is if you've got a dilation from the y-axis, it's always 1 over, whatever that is. Right, so from the y-axis, it's always 1 over whatever that number is. Right, from the x-axis, it's just what the number is, but from the y-axis, always 1 over. And if you remember it, dilation from the y-axis is always 1 over that factor, then you can't go wrong. So it doesn't matter whether it's an exponential, whatever it is. It's always a number in front of the x, dilation from the y, 1 over. All right. Anything else that I need to
Is that all?
answer?
Don't
That's
you even
it.
have to sketch a graph?
Not of this one, no.
That's good.
All right, follow V.
So would you have to write the answer as plus
There you go.
like this? Or could you just write,
There you can just write dilation from the y, just factor that. All right, because we want to know what the transformation is. What is it? It's a dilation. Well, it could be from the x or the y. This one's from the y. What factor is it? That.
that was 5e?
That's 5e, yep.